one of the questions we've been asked on Machine Mondays is to include more of the testing rather than just the machine. So today we've come in the lab, do a bit of a different test, and we're going to focus on this machine, which is measuring tensile strength and elongation of the compounds that we make and the finished cables. So at the minute the lab are testing some Earthshore 2-core 2.5. We have samples in the desiccator conditioning them, and these samples will be pre-cut lengths of the cores, which are then these circular tubes, or if we were doing the sheathing, we actually skive the samples down and make these dumbbells. The way this machine works is we put the test pieces into the tensometer and we can grip them. There's a load cell at the top, and then there's measuring devices in the middle. So as the cable's then gripped and they stretch, this load cell will measure the amount of force that's being applied, and then it gives you a measurement of the force at break in newtons per millimetre squared. And these devices go up and they measure the distance travelled, so that will then translate to the elongation percentage at break. To understand it properly, we need to understand the aging method. So we have to do this test before with the samples unaged, natural as they are in the cable, and then we also have to age the samples, so we're replicating its lifespan, and then we test them after aging and before aging. We measure the difference, and they have to be in a strict tolerance of variation unaged to aged. So we'll take you to show the aging oven. So these are the aging ovens. Look a bit spaceship-like, but what happens is there's a different cell for each material. So we can have a blue core, a brown core, sheathing, etc. We've got a variety of aging ovens because the tests are all done at different temperatures. So depending on the compound, some will be aged at 80 degrees Celsius. If it's heat resistant, it'd be 135 degrees Celsius. And then it could be 7 days aging or 14 days aging, all depending on the material. But if we take a closer look inside here, we'll see how the chamber comes up, and the cores that we looked at on the Earthshore are sat in the aging oven cell, and whilst they're in there they're being heated up, and a specific number of air changes is happening inside the cell, and air's passing over it and replicating the cable being used over its life and aging the compound. When we're testing these samples, we're measuring the force at break. So to do that we need the cross-sectional area of the compound that's in there, and then the load cell measures the force required to give us a result in newtons per millimetre squared. So if I go to these test reports that have already been done and we look at the blue, we've already got the cross-sectional area of this blue conductor. So the insulation material there is 6.11 millimetres squared. So we can input that into our test and then set it running, and it'll give us a result. So when that test is finished, we can accept the result, and it will then tell us the tensile strength at break, which on this sample was 13.76 newtons per millimetre squared, and the elongation is around 183%, which is well above the tolerances that we've got on this particular compound. So that's now 5 tests done. We do 5 tests on the unaged, and then we do 5 tests on the age, and we measure the difference. We're taking the median result, and what we're really looking for is the overall results, which are a lot higher than what we expect. So this strain at break, the elongation at break, in a normal twin and earth it'd be 125%, and we're up at the 182% mark. But we're looking for this consistency of results. So we're looking for consistency on the test samples, they're all breaking at the same time, and then we're always setting that high bar of quality and trying to get a higher percentage than what the minimums are in the standard.